Okay, so today we're going to move on to our next lesson in our solutions unit, and we're going to focus in on polar molecules and electronegativity. So for this lesson, you're going to want to have the table of electronegativities handy. So I included that a few days ago as a PDF document. There were sort of two tables that you're going to refer to in this part of the unit. So it's not the greatest copy, unfortunately, but this is what the table of electronegativities looks like. So if you want to get that out, we'll be referring to it throughout the lesson. So it would be good to have it handy. Okay, so this is going to tie back a little bit to the properties of matter unit, but we will go through and re-explain the concepts that we need from that unit. So we learned that water is a strongly polar molecule. Okay, so what polar means is that there's a separation of charge within the molecule. So don't worry too much about this 104.45 degree angle here. What's most important here is that we've got a negative end to a water molecule and a positive end to a water molecule. So what happens is this is a covalent, these are covalent bonds, and we know that covalent bonds share pairs of electrons, but the pairs of electrons aren't always equally shared, which means there's some atoms that have a stronger pull on those shared electron pairs. So in the case of water, oxygen pulls more strongly on the shared pair of electrons and pulls that pair towards the oxygen atom. So that means that the electrons spend their time close to the oxygen and not so close to the hydrogen. So that makes the oxygen end of the water molecule have a partially negative charge. So when I say, this is what that looks like. This little symbol means partially negative. Okay, so if the electrons are being pulled over here, that leaves the hydrogen end partially positive. Okay, so sometimes you'll see water drawn like this. The oxygen atom is larger, we know that, larger than the hydrogen atoms. And then the hydrogen atoms, so it almost looks like kind of like Mickey Mouse ears. So the Mickey Mouse ears are the hydrogens, and they're positive. And I mean, it's an upside down Mickey Mouse, but you could draw it in any orientation you wanted. And then the oxygen has a negative charge. So this means the oxygen end of a water molecule has a negative charge. Okay, so the reason we talk about polar molecules, in particular water, in the solutions unit is because most of the solutions that we make are substances that have been dissolved in water. So the fact that water is polar is really important because it being polar plays a large role in how easily things dissolve in water. And we'll get into that in a minute. So we call this type of bond a polar covalent bond. Okay, we know that these are covalent bonds, they're sharing electrons, but the sharing of electrons is not equal. Hence, we get the negative and the positive. So it's found in many molecular compounds. Polar bonds form because electron pairs shared between atoms are not always shared equally, which I already mentioned. Some types of atoms attract electrons more strongly. The measure of how strongly an atom attracts electrons is called electronegativity. Okay, so some atoms have a higher electronegativity, which means that they have a stronger pull on those electrons. Okay, so the most electronegative atoms on the periodic table are fluorine, nitrogen, and oxygen. Molecules that contain these atoms and are molecular compounds are quite often polar. Okay, so this is where I'm just gonna flip over to this table of electronegativities just to show you what this looks like. Okay, so here's our periodic table. You'll notice our noble gases do not have electronegativities because they're never involved in compounds, right? They're stable, they don't take part in any sort of pairing of atoms. So if you look, you'll notice the metals on the left-hand side have lower electronegativities in general, and the non-metals have higher electronegativities. Okay, and actually what happens is the trend is if you go across a period, you'll see that the electronegativities increase. And if you go from the bottom of a group or family upward, you also see an increase in electronegativities. So that means these guys over here in the top corner are the three most electronegative atoms on the periodic table, with fluorine being the most electronegative. So when something combines with one of these three, the electronegativity of each one of these three is so much larger than whatever its partner is that it has a much, much stronger pull on those shared electrons, and it pulls those electrons towards it. So these three would end up with that, you know, partial negative charge in the polar compound, and whatever they were partnered with would have the partial positive charge. So let's just go back and kind of to our notes and look at this here. Okay, so here's another example of a polar molecule, hydrogen chloride. Okay, so we've got hydrogen and then we've got chlorine. Now chlorine isn't one of the three we listed, but it still has, it's right underneath fluorine, right? It's right underneath here. So it's still going to have a very high electronegativity. Hydrogen's way over here, and it's got a lower electronegativity. Okay, so because of the difference in electronegativities, chlorine is going to pull the electrons closer to it. Okay, so you end up getting a negative charge on chlorine and a positive charge on hydrogen. Okay, so this chart just shows that pattern I explained. So it shows the pattern of electronegativities. Okay, and it shows that non-metals have stronger or higher electronegativities than metals. Now, so what do those values mean? How can we actually use those values? So when you're trying to figure out if something is polar or not, you look at the electronegativity values and you subtract them. And you always subtract the smaller electronegativity from the larger one to get a positive answer. If the difference in the electronegativity values between the two different types of atoms that are forming the covalent bond falls within the range of 0.4 and 2, the bond is considered to be polar covalent. So let's just look at some examples so we can see how this works. So let's say we have a bond between hydrogen and sulfur. Okay, so the values are here, but I'm just going to pull up that chart again so you can see. Okay, so here's hydrogen with a value, an electronegativity value of 2.2, and sulfur is over here, and it is 2.44. Okay, so now for some reason on the notes it says 2.5, so let's just fix that. Okay, so if we go down here, we've got sulfur. Let's just fix this. This is actually 2.44. You'll find sometimes the values, the electronegativity values vary slightly depending on which table you use. So like they're not wildly different, but they can be a little bit different. So the 2.5 was likely taken from another table of electronegativities. And here's hydrogen. So if we subtract 2.2 from 2.44, what we get is 0.24. Okay, so the difference in values is 0.24. Well, that is not within this range. It's lower than 0.4. So therefore, that's not a polar bond. It's not a big enough difference to result in the electrons being pulled more like super close to the sulfur versus the hydrogen. They'd be roughly equally shared. The difference isn't significant enough. Okay, we consider the difference to be significant enough as soon as it hits 0.4. Okay, so let's just look at water, for example. So I'm going to flip back to the chart, make sure our values are correct. So we've got oxygen at 3.5 and hydrogen at 2.2. So let's just go back. Okay, so here's oxygen at 3.5, here's hydrogen at 2.2. If we subtract them, we get 1.3. Well, that falls right within that range, therefore it is polar. Okay, so you can use those electronegativities to determine whether the molecule is polar or not. Okay, so because water molecules are considered to be highly polar, and the reason they're highly polar is because oxygen is one of the most electronegative atoms on the periodic table. That highly polar characteristic causes them to make excellent solvents, which means many compounds are able to dissolve in it. Okay, so why would that be? So let's just take a look at why that would have any influence on whether something can dissolve. So normally if we were in class, I would show you this demonstration. You can actually try this at home. All you need is some sort of insulator, like a piece of plastic, or like a plastic ruler would work. Yeah, that would probably be your best bet if you have, or like a strip of, like even if you had like a little PVC pipe, something made out of plastic is probably your best bet. And you just need to charge it. So rub it on your sweater, rub it in your hair. You're just charging it like you would, you're trying to get a static electric charge built up. And what you do is, if in your tap, you let a thin stream of water drip down from the tap, just like a very thin stream. And if you bring that charged ruler or rod or whatever it is that you have close to the stream of water, you'll see that it bends, and it bends towards the strip. So I actually, in the Edmodo post today, I included a link to a video that shows this. So if you don't have the materials at home to try it yourself, you can watch the video instead. So what I'm going to draw here is we've got some sort of strip. Let's say this is like our plastic ruler. Okay, now we aren't necessarily sure if when we charged this by rubbing it on our hair or our sweater, if it lost electrons or gained electrons. We're going to just assume that it lost electrons and became positively charged, but it really doesn't matter. If it was negatively charged, you'd just see a different orientation of the water molecules. So the water, I'm going to draw water like I showed you before, like a Mickey Mouse. Okay, so this time I'll draw Mickey the right way up. Okay, so these are our positive hydrogens and our negative oxygen. So that's our H2O. Now, we know that opposite charges attract. Okay, so because this is polar and we've got this charge separation, the negative part of the water molecule will be attracted to this positive strip. So what you'll see is when the water first, if I draw my water molecules, okay, So they could be in any orientation at first, but when they get near the strip, the negative end will be attracted and the positive end will repel. Okay, and you'll end up seeing the water bend. So it will be going straight and then it takes an obvious bend towards the strip. Okay, so sort of like that. So instead of just falling straight down, it makes a bend towards the charged strip, and that bend is an attraction between positive and negative. Okay, so how does that affect dissolving? So I also included another link to a video that shows you the difference between dissolving an ionic compound and a molecular compound in water. So the explanation just shows dissolving salt, sodium chloride, versus dissolving sugar. We know both substances dissolve, so if you put in a spoonful of salt into water and stir, eventually it'll dissolve. Same thing if you were to put a spoonful of sugar into water, it will dissolve. But the process by which the two things dissolve looks a little bit differently. So the video actually does a really good job of diagramming out what happens. So take a look and check that out. And then we'll just go into more detail here. So let's start with dissolving ionic compounds in water. So we'll also look at how sodium chloride, which is ionic, dissolves in water. So like we've said already many times, water molecules are polar and they have a negative charge around oxygen atoms and a positive charge around hydrogen atoms. So when you place sodium chloride in water, the water molecules completely surround the surface of the sodium chloride crystals. The positive end of water molecule move toward a negative chloride ion. And the negative end of the water molecules move towards the positive sodium ion. The forces of attraction between the water molecules and the chloride and sodium ions in the sodium chloride crystal breaks the ionic bonds in the salt. Okay, so I'll just finish writing this out and then I'll go back to the diagram and talk about what's happening. So the chloride and sodium ions are broken off the crystal and surrounded by water molecules. The salt is dissolved by this process. And we call this process, when those ions fully separate, we call this dissociation. Okay, and if the solvent is water, which often it is, this process is called hydration. We don't tend to use the word hydration very often. You'll more commonly hear this referred to as dissociation. Okay, so here we go. So this is our crystal of sodium chloride. Okay, so this gets dropped into the water. Okay, and the fact that water is polar makes this process of dissolving quite easy because we have this attraction. Okay, so water molecules surround this whole crystal, okay, and what they do is when they start to surround the salt, we get this attraction happening. So here's our Mickey Mouse water molecule. Positive is the blue hydrogens, negative is the red oxygen. So because in an ionic compound you have positive ions and negative ions, right? This would be your sodium and this is your chloride ion. What happens is the negative part of the water the negative part of the water molecule, the oxygen part, attracts to the positive ion and it pulls that positive ion away. So you get that within the solution, you get a complete separation of these ions, right? So they're all completely separated out, and each individual ion is surrounded by water molecules. Now, the number of water molecules surrounding is not important. This is just a diagram to show how they would surround it. So you can see here's our positive sodium. Pointed in towards the positive sodium is the negative part of the water molecule. So it attracts the negative oxygen portion of water and it repels the positive hydrogen portion. The opposite is true over here. So when you surround the negative chloride ion, you'll see the positive hydrogen is attracted inward and the negative oxygen is repelled outward. So that fact that water is polar, that attraction is what breaks those ionic bonds and separates out those ions in the process of dissociation. Okay, so our final thing is just going to be to compare this to dissolving a molecular compound. Okay, so a molecular compound, when a molecular compound dissolves, the intermolecular forces between different molecules are broken and the entire molecule is pulled away from the solid crystal. Not all molecular compounds are soluble. So that just means some dissolve and some do not dissolve in water. But polar molecular compounds are soluble in water. Okay, so let's just kind of look at this diagram and see what the difference is. And then we'll talk about why the polar ones are soluble and the non-polar ones aren't. Okay, so here's our sugar. Okay, and each one of these gray circles is a sugar molecule. Now, we know sugar is, we do glucose, C6H12O6. Okay, now notice we're not breaking the sugar up into carbon, hydrogen, and oxygen because these aren't ions, right? They're not charged. These are joined together by sharing electrons. Okay, so there's no charges involved here. But what does happen is the polar water pulls each molecule away. Okay, so this would be like a lump of sugar. Now, each one of these is a molecule of sugar. So the polar water molecule pulls each molecule of sugar apart. So it's still dissolving, but the entire molecule stays intact. Okay, so it's not separating out into its individual atoms. It's staying whole, and each whole molecule is surrounded by water. Okay, so that's different from ionic. Ionic split up into its separate components, which were charged ions, and then each charged ion was surrounded. Here, the entire C6H12O6 stays intact, but each individual molecule as a whole is pulled away and then surrounded by water molecules. So this is just sort of simplified. We're not showing any sort of charges. So even though this could have a positive and a negative end to it, this is just a simplified view, okay? Each molecule surrounded by water. So down here, I want to show you why a polar molecular compound is soluble in polar water. So what is actually happening if we were to sort of zoom in? Okay, so let's just say water dissolving a polar molecule. Okay, so let's say the polar molecule, I'm just not going to give it a particular name. Our polar molecule looks like this. Okay, and this is the negative side of it, and this is the positive side. Okay, so the reason why it's easy for a polar molecule to dissolve in water, with water being polar, is because of that same charge attraction. So on this end, you would get this orientation of the water molecules. Remember, the Mickey Mouse ears are the positive hydrogen. So the positive hydrogens are attracted to the negative end of the polar molecule. And then you'll see a different orientation of the water down here by the positive end. So the negative part of the water is now attracted to this positive end, kind of in this fashion. Okay, so that's why polar substances dissolve in polar water, because it's that opposite charges attracting that pulls the molecules away, and this is how the water molecules would orient themselves. So make sure you check out the videos that I attached, and you can work on worksheet 2, and you can just use your notes to help you answer the questions.